Welcome all of you. In the last lecture, we have discussed about basics of shear strength and stress representation in different form. Now we will get into the shear strength of soils specifically. While doing so, we will divide the soil into two. The first one will be for cohesionless soil and the other one is for cohesive soil. This is divided in this form because the shear strength behavior or shear strain behavior of these two classes of soils are entirely different. While you know that for cohesive soil, it is generally influenced by the drainage condition and pore water pressure. We will see that in detail. Whereas for cohesionless soil, the drainage, it is almost draining soil. So, the question of undrained condition does not come into effect except for some very specific problems like liquefaction. So, we will now first get on to the shear strength of granular soils. Now, we can see that all soils are granular in nature. What is so specific about it? But here when we discuss about soil mechanics, we will refer granular soil to essentially cohesionless soil, which will include gravel, sands or cohesionless silt size geomaterials, because this will include materials like fly ash, which are essentially silt size and hence they can be considered as geomaterials with less or no clay content. So, here when we say granular soil, it essentially refer to cohesionless soil. It does not possess true cohesion, that means it is the absence of natural cementation. But some granular soils like sand, it can exhibit what is known as apparent cohesion, which is condition specific. It depends upon the water content or the degree of saturation of that particular sand. You might have noticed that it is fairly comfortable walking on beaches which are partially wet. Why this is so? This is mainly because of the capillary action or the negative pore water pressure, which we call it as soil suction, which is present in partially saturated sands. Hence, it imparts more strength and hence you are able to walk comfortably on beaches. But that is not the case with dry sand or fully wet sand. So, this is known as the contribution or this additional strength which the sand possesses under partially saturated condition. This can be termed as apparent cohesion. So, we are not considering about apparent cohesion right now. What we understand is cohesionless soil, there is no true cohesion. So, since we understand that for cohesionless soil there is not much influence of drainage and there is no cohesion coming into picture, the understanding shear strength behavior is relatively simple as compared to that of cohesive soil, which we will see later. So, we can conveniently write shear strength of granular soils tau f is equal to sigma dash f tan phi dash, where tau f and sigma dash f, these are stresses acting on the failure plane, which we have already seen in the previous lecture, and phi dash is the angle of internal friction. Please note that tau f, there is no prime, sigma dash f, that is for normal stress, it is always in terms of effective stress. Phi dash is mostly determined by either direct shear test or drained triaxial test. because the permeability of granular soil is fairly high. The initial state of the granular soil, whether it is a loose, medium or dense state, affects the shear strength. Now, what is this initial state? Now, initial state depends upon the initial unit weight or packing or the compaction state, and is generally defined by the term relative density, which all of you knows. So, as a guideline, a relative density less than 35% is considered to be loose, 35 to 65% is medium, and greater than 65% is considered to be dense. So, we are basically discussing about 3 states of the granular soil, which we define in terms of loose, medium and dense. So, this relative density takes care of what is the kind of initial packing of the granular materials. So, now we will see the typical stress strain response of sand, which is a granular material, from a typical direct shear test, wherein the x axis is represented by lateral shear displacement and y axis is given by nominal shear stress tau. Now, we know in direct shear test it is very difficult to quantify the strain and the true stresses acting on the failure plane or which is acting on a given plane. The reason is the area of direct shear keeps changing during the test, because there is a horizontal movement of the upper box. So, it is very difficult to state the true stresses acting, and hence the term nominal shear stress tau. And instead of strain, we express this in terms of lateral shear displacement, or it is written in terms of relative displacement. Intentionally, we do not use the term strain there. So, here there are 3 states we have discussed. We can see that the stress strain response is drastically different for dense, medium and loose. At least dense and loose, it is fairly different. What is happening? We can see that for a dense soil or the dense state of the soil, initially there is an increase in shear stress, reaches a maximum value, and further which it starts reducing. Now, this post peak reduction is what is known as strain softening. So, there is a maximum shear stress or peak shear stress in the case of dense packing. Medium, it reduces, but for a loose state of packing, we can see that there is an increase in stress, but there is no reduction in stress. Somewhere at some point there will be yielding of the loose state. So, even after yielding, we can see that the stress keeps on increasing, and all of these finally reaches to a relatively constant value, which is known as critical shear stress, tau CV, or constant volume shear stress or critical shear stress. So, whatever be a dense reaches peak, strain softens, and a loose keeps on densifying and reaches finally a critical state. So, this is the general understanding of stress strain response of sand. Now, the same type of behavior is applicable for cohesive, but in a different framework that we will see when we discuss the shear strength of cohesive soil. Now, what is happening is, this is what a loose state represents. That means, soil particles are loose, and when this loose state is subjected to shearing, that is the horizontal movement, what will happen is, when the loose state of the granular soil is sheared, particle can move horizontally, and when it moves horizontally in this direction, what happens is the particles moves downwards. As you can see, the arrow all these particles goes and fill into the voids because it is a loose state, and hence it moves downwards. This is very important aspect which we need to understand. When a loose state is sheared, particle moves horizontally and downwards, as it can be shown by the arrow, and hence it undergo compression during shearing. This is an important point which we need to keep in mind. A loose state, when it is sheared, undergoes compression. This is very important observation. In the case of dense state, it is already in these voids. So, there is a good interlocking of materials. Now, let us say that this dense state is sheared. Now, for shearing means it has to move horizontally. Now, what is the possibility of such a movement? If it has to move horizontally, then it has to undergo some movement. So, that we will see. So, the dense state of the granular soil is sheared. So, it is sheared. Shearing is restrained by interlocking because it is already occupying the spaces, it is densely packed. So, there is a good interlocking. Now, during shearing, if it has to move horizontally, then it has to move in the upward direction. The particles have to move in the upward direction. So, this is different from the loose soil. So, movement up the inclined plane than horizontally. So, if it has to make any sort of horizontal movement, the movement of this particle is more like moving up the inclined plane. So, it has to do additional work. Now, this causes expansion or what is known as dilation. Please remember this carefully, like when a dense state of soil is sheared, for executing shear it has to expand or it is known as dilation, and during dilation there are formations of loose pockets, because a dense material which is packed, when it expands, definitely it leads to the formation of loose pockets. So, this is the change in behavior, or this is the difference in behavior when a loose and dense state of the material is sheared. Now, let us see a loose state in detail. Soil particles moving horizontally can be idealized easily by Coulomb's friction model, as what we have learnt, because here it is loose state, there is an intergranular contact where tau of sigma dash f is acting. This is the predefined failure plane along which it acts. We know the Coulomb's friction model is applicable only when there is a failure plane attached to it. So, we can easily write tau f is equal to sigma dash f tan phi dash, no confusion in that. So, let us see for a dense state what is going to happen. Soil particles moving upwards during shearing can be idealized by a block moving up the inclined plane. Now, it is already in an interlocked position. So, it is more like this. So, the plane now is inclined at the point of contact, or tangent plane is inclined. So, same interpreted on an inclined plane upwards. So, what is happening? It can be idealized by the block which is moving up the inclined plane. So, you can see that there is an incline, there is a block here, the weight of the block acting downwards, r is the resultant, phi dash is the angle, and here the slope angle is alpha. Now, this is a very prominent friction problem that we have learned, and we can conveniently write tau f is equal to sigma dash f tan phi dash plus alpha, because it is movement up the inclined plane. Now, if it is down the inclined plane, this will be minus. In soils, both will be there. There can be upward and downward movements for particles, but generally in the case of dense soil, for explaining the shear behavior, we normally refer to dilation or expansion. The expansion or dilation in dense state increases the friction angle component. This is what it is. So, it increases from phi dash to phi dash plus alpha. The additional component alpha is called the dilation angle, very important. Now, imposing high normal stress. Now, if the normal stress is more, let us say, what happens is this particle will not be able to traverse in the upward direction. You are restricting the movement from the upward. There is a confinement. Now, this confinement will not allow the particles to move upwards freely, which means to say that the amount of dilation that is going to happen is a function of the normal stress. Now, in this case, normal stress is more like a confining stress from above. So, imposing high normal stress suppress the tendency to dilate, because of which the dilation angle decreases. Now, we will see this again. There are some facts which we will enlist, where dense and medium compacted granular soil exhibit peak shear strength, specifically at low confining stress, because the dilation has to happen. Then only the dilative behavior, expansion followed by the peak behavior is going to happen. So, this peak which is marked here is a function of this dilation behavior. So, peak behavior occurs at low strain or relative displacement due to particle interlocking and dilation, and it is mostly a stiff response, which means particles are tightly held. So, it is a stiff material. Now, the peak happens at a low strain. So, it keeps on increasing, reaches a peak, but this peak behavior is exhibited at relatively lower strain, not at a higher strain, and or it is expressed in terms of relative displacement, whatever, and this happens because of the dilation or particle interlocking. On further shearing after the peak, stress comes down to critical state or tau Cs or tau Cv, or it is known as the ultimate state. We have already told this particular movement downwards, not movement, the stress comes down. Okay. So, this post peak reduction is called strain softening behavior. Now, critical state, which is the state here, or constant shear strength, occurs at large strain. Generally, it is 10 to 20% relative displacement. Now, this is again defined in different codes. It is generally 10 to 20% of strain level. You can expect critical shear strength. Loose state does not exhibit peak and directly approaches tau Cv, as can be seen here, it directly approaches tau Cv. The progressive increase in stress after yielding, post yielding, is called strain hardening behavior, which is denoted here. Now, that is about the stress strain behavior, whatever we have discussed. Let us see what happens to the volume, because we do not generally discuss about undrained or no volume condition. For granular soil, there will be volume change, and how it happens for dense and loose state. We will see that. The volume of dense sand decreases initially and then dilates. So, here on the y axis it is vertical displacement, and on the x axis it is lateral shear displacement or relative displacement. Now, for the dense soil, we can see that there is an initial decrement in vertical displacement, which is nothing but compression. So, below is compression, no volume change and expansion. For dense soil, there is initial compression followed by an increase in volume, which we call it as dilation. So, by the time it dilates, it reaches the peak behavior. Volume reaches constant at high strain, relative displacement. So, by the time it reaches the critical state, the volume change also remains constant. There is no more volume change. It reaches a constant volume or a constant value at high strain condition, maybe close to critical state. Loose sand undergoes progressive compression, or it is progressive densification, till it attains critical constant volume or critical state volume, that is also at a high strain. In direct shear test, the area keeps changing, hence true stresses and strain are difficult to determine, which I have already explained. Shear stress developed on shearing surface is non-uniform for direct shear test, because at the edges and towards the center it will not be same. Now, for dense soil, the total friction angle can be written as phi dash peak is equal to phi dash mu plus alpha. We have already discussed what is alpha. Now, peculiarity about alpha is it increases with an increase in relative density. We have seen that depending upon what is the relative density, the dilation keeps changing. So, that will be reflected in alpha. So, alpha becomes a function of initial state or denseness. If it is more dense, alpha will be more. Now, phi dash mu, this component is due to the friction mobilized at intergranular contact, that is the particle interaction, and this is somewhat a fundamental aspect of a soil, phi dash mu, which is mobilized at the particulate contact. Alpha is the effect of interlocking dilation and hence a function of normal stress sigma dash f. So, in this total friction angle of dense soil, phi dash mu is a function of particle interaction, alpha is a function of dilation. Now, since alpha is a function of dilation, we have already seen that alpha is a function of normal stress. If normal stress is more, it suppresses the dilation. So, we will see the effect of sigma dash f on alpha and Coulomb's failure line, how it changes the Coulomb's failure line. This is tau versus sigma, which we normally represent the shear strength behavior. For a cohesionless material, this is Coulomb's failure line without dilation. So, this is phi dash. So, it is very easy to understand. OP is the failure line represented by Coulomb's model. As sigma dash f increases, the dilation is suppressed. So, when corresponding to sigma 1 f, let us say it is a dense soil. So, it will have the dilation angle of alpha 1 corresponds to a tau peak 1. So, that is the first state. Now, let us say that for a as the normal stress increases, for example, at sigma 2 f, what is happening? We can see that the dilation angle gets reduced. Now, this is the phi dash. Now, that is what is denoted by phi dash mu. Now, what is above that? Above phi dash is alpha 1, that is getting added. So, this is alpha 1 at lower normal stress, alpha 1 is more, but as sigma 2 f it increases, this alpha 2 is less than alpha 1, which is denoted by point r. So, this results in a curved Coulomb's failure line, which is due to dilation. If you join through these points, then you will get a curved line. Alpha reduces with sigma dash f and hence results in a curved failure line, which is represented by OQRS. And at some sigma dash f, that is along this x axis, there is a complete suppression of dilation. So, if you keep on increasing, so there will be another point here. At some point here, there is a complete suppression of dilation and alpha tends to 0, and the failure line, it merges with the initial failure line, where Coulomb's failure line without dilation is there. So, alpha becomes equal to 0. At this particular point, alpha is 0 and phi dash peak is equal to phi dash mu according to this equation. So, alpha is 0. So, phi dash peak is equal to phi dash mu. So, dilation angle alpha is the measure of change in volumetric strain with respect to change in shear strain, and phi dash mu can be termed as friction angle corresponding to critical state or constant volume. We have tried to understand what is phi dash mu. Now, what is the significance of this phi dash mu? Because this is the fundamental aspect or the fundamental friction behavior of the soil. Whatever be the state, there will be some kind of friction angle, which is the critical state friction angle. We will be able to appreciate this better when we finish the 4th module on critical state. For the time being, let us understand that there is always some value which remains and which can be mobilized by a soil, that is a critical state, and phi dash mu is termed as the friction angle corresponding to critical state or constant volume. So, phi dash Cs is equal to phi dash mu. Now, whether dilation happens or not, that will determine alpha or the additional component that gets added to the soil. So, shear strength corresponding to peak behavior is called peak shear strength, that is tau peak, and it is expressed as tau peak is equal to sigma dash f tan phi dash plus alpha. Strength corresponding to critical state is called critical shear strength tau Cs, which is given by tau Cs equal to sigma dash f tan phi dash Cs. Now, remember this is critical strength friction angle, and phi dash peak is equal to phi dash Cs plus alpha. Earlier we have written in terms of phi dash mu, that is for our initial understanding, but where it boils down to? It boils down to phi dash Cs. So, Coulomb's failure line without dilation, and here this friction angle, which is the friction angle which is mobilized by soil at any state, that is phi dash Cs. On top of it we get alpha, which is phi dash peak. Alpha generally ranges between 0 and 15 degrees. Phi dash Cs is the effective friction angle at critical state shear strength, a fundamental soil parameter. This aspect of fundamental soil behavior can be better appreciated again when we discuss this aspect in module 4. For a plane strain case, Bolton in 1986 showed that phi dash peak is equal to phi dash Cs plus 0.8 of alpha. Here we have taken plus alpha, but there is not much of difference, but specifically for plane strain condition Bolton explained this to find out what is how the dilation angle contributes to phi dash peak. So, that is all for now. We will see in the next lecture the remaining portions of shear strength of granular soil, wherein 3 aspects we will be discussing. One is the critical void ratio, then we will discuss about Taylor's model, and there is something called intrinsic friction. So, these 3 aspects will be covered in the next lecture. Thank you.